So this lecture, we're going to talk about hardware and software systems. Internet of Things devices are typically hardware and software combined. So as we're learning about the IoT design process, we really have to think about how you design hardware, how you design software, and how do you design them to work together. So you can't think of one in isolation. You need to really think about both together as you're working on the project. So IoT devices are a combination of hardware and software. There's always a hardware part of the design, and you can see that here. We've got a breadboard, and the breadboard's got various components on it. It's got a microcontroller, LED, voltage regulator, capacitors I see, a bunch of different things, and they're all mounted into this breadboard. One part of this design, one aspect of the design, is the hardware aspect that you can see right there, and that's basically a bunch of components that are connected, wired together in some fashion. Okay, so that's part of the design. And so a designer, if you're going to make an IoT device, you have to think about that part too. But in addition to that, that alone doesn't explain what the behavior is, meaning looking at that set of devices wired together, even completely understanding what each component does, you can't tell what the behavior of that, right? So you have an incomplete view of the design if you only look at the hardware. In addition to this, you've got to look at the software component of this too. So if you look at the hardware side over there, you've got at the center of it, there is this microcontroller, that big black chip dead in the center. That is the microcontroller, which is the heart of the system. And that microcontroller executes code. And so there's got to be some code, some software, which we can see on the other side of the picture, some software that's going to run on that microcontroller. Now that software is some sample code, and that's actually Arduino code, and we'll get to that later. But there's got to be some software that's running on that microcontroller that talks to all the different components, talks to the LEDs, tells them when to turn off and on, and things like this. So there's this hardware side and this software side, and these things have to work together. You've got to design both of them. So what I mean is when you write the software, you have to be thinking about the hardware. You have to say, oh, I've got an LED and it needs to be controlled in this fashion, so I will write my code this way. You have to be consciously aware of that when you're doing the coding. Whenever you make a new project, you've got to have a bunch of hardware components, right? You've got to get a bunch of hardware components, wire them together, and decide on that a priori. What are the hardware components going to be? Now, this is sort of a fundamental issue with design projects in general. Things change, right? So at first, when you design something, you have an idea of what the behavior is going to be, and you think you know what the components will be. And then you start doing it, you get into the design, and often you have to backtrack. You might implement something and realize, oh, you know what? I need a different component. This doesn't work for me. So that can happen. There's always that risk. But at the beginning, to start building your system, you are going to have some idea of the type of components that you're going to need. So that's always a trial, right? To figure out which components you're going to buy. Now, you start with a microcontroller, but you need other components around that. And each one of these components has different parameters, different sizes, for instance, and you might care about that. You might need this whole design to fit in a certain space, right? So you're worried about the size, different voltage, different electrical parameters, right? How much current can this component take, right? Maybe this LED can only take 20 milliamps, which is sort of common. So if you drive it with more than that, you'll blow up the LED, things like this. So every one of these components has these features that you have to consider before you order them. Now, back in the old days, it used to be, back in the old days when I was a kid, when you wanted to do one of these projects, you would go to a store, Radio Shack, which is gone now, or effectively gone. You go to Radio Shack, and you could buy the parts. And the people in the store could help you with the parts. So they were knowledgeable about these little parts. So they would say, oh, that chip, it will do this, but this component, this resistor is no good for that purpose. It's something, right? They have knowledge about the different components and what they did. But those components don't cost a lot, right? Switches and things like that, they're very cheap. So stores like Radio Shack, things like that, they don't particularly care about selling those things anymore, frankly. I mean, they sell them, but it's sort of, they don't make a lot of money off of them, I get the feeling. They make money off of selling cell phone deals or something like this, something else. So you go into these stores, and generally the people are not knowledgeable about their components, which means that it is on you to understand these components and what they do. So you can't rely most of the time, unless you go to a good store, and there are stores like that where you can get somebody who really knows what he's talking about or she's talking about, but often you are on your own. And another thing too is that these type of hobbyist electrical stores, they are rare. They are few and far between these days. You can't find stores that have these parts. I mean, I go to Fry's, things like this, also other local places, but it's hard to find these parts. So often you're buying these components online. You go online, you look at websites. Now these websites There are a lot of different websites, and they're very complete. They have tons of components. But in some ways, it's sort of data overload, right? There are too many components, too many slight variations. So you see 100 components that look similar, and you have to figure out exactly the one that you want. And I can't tell you how many times I thought I wanted a component, I ordered the component, it comes a week later, and then ta-da, it is not what I needed. It is somehow slightly wrong, and now I have to go and order new parts and cycle through that. And it is inevitable that that will happen to some extent. So just be ready for that. But you really want to minimize that. You want to be able to know before you go and order these parts, you want to be able to know that they match your needs as well as you can know that. So that is what data sheets are for. So data sheets are basically information sheets about hardware components. And every component has a data sheet. The simplest components, maybe you don't have a data sheet. For instance, a resistor. Actually, even resistors, you can probably find data sheets. But a resistor is so simple, you don't need a data sheet for that, okay? They have very few parameters. But any kind of complicated component will have a data sheet that tells you all kinds of information about it. The size, the shape, the inputs, the outputs, the voltage, all the electrical parameters, things like this, all the data that you need in order to use it. So reading these data sheets is really important. You can always find data sheets online. You find the part number, you type it in Google, type it into Google, the part number, type data sheet, and you will find data sheets. And they can be very complicated to read, but it is important that you be able to minimally read them, at least find the important information, just so you can order the parts that you're going to need to make these devices that you will be making. Thank you. So we'll continue to talk a little bit more about data sheets for hardware components, specifically for integrated circuits, because they are extra complicated. So right here, we've got this is a rectifier, Schottky rectifier. This is a piece of a data sheet. So if you Google Schottky rectifier, and if you type in the part number for that, and type data sheet and Google that, you'll come up with a data sheet, several versions of it actually, and you can click on it, and there are lots of different things inside this data sheet. One thing that you always find inside a data sheet is the physical dimensions of the part, because they always want to tell you how do you build it into a bigger system, right? So how's it going to connect to everything? You always want to know that. So this is actually a diagram showing the physical dimensions. It shows all detail, right? The size of it, and actually this is just one cross section. A lot of times these data sheets will show different views from different angles. But this shows you the width of the pins. It shows you every dimension that you need to know about. And actually right there you can't see all the numbers there. They label them with letters, but there's a table next to it that shows what the sizes are. This is a typical thing that you'll find inside a data sheet. Now you find tons of information in a data sheet. And part of it, certainly when I started, I could not read most of a data sheet. All right, you can read a little bit of a data sheet. So I don't expect people to be able to read the whole data sheet. And in fact, most of the data sheet you don't practically need. But some key things you should be able to figure out. So for instance, the size, right? You typically want to be able to read the size, because there are certain things that you need to know. Like for instance, for this class, when say you want to use a breadboard, right? That's commonly what we want to use for prototyping, is a breadboard for connecting things. For that, you need to know the size of the pins and the spacing between the pins, because the holes in a breadboard is spaced at 1/10 of an inch between each hole. So when you get a component, you want to know that the pins are spaced some multiple of that so you can fit them into the breadboard, things like this. And if they're not, you need to know that before you order the part so that you can do something about it. So the physical size and physical dimensions, you always find that in a data sheet, and you'll need to be able to read that. Now, other information, just a sample of some of the other information in the data sheet, you find electrical parameters and thermal parameters, what temperature can this thing run at. Now, usually thermal parameters are not something I generally need, because I'm not trying to use these components in some extreme environment, but they give some kind of boundaries. Can't be hotter than this, colder than this. That's generally not useful to me, but maybe you're using some application where you need that information. Electrical parameters are important to tell you things like what's the maximum minimum voltage, maximum current that can go through that, and that is actually important because you want to make sure, for instance, that components are voltage compatible. So for instance, say you get a microcontroller and it's outputting at 5 volts, but you get a component that only accepts up to 3.3 volts, which by the way is a common mismatch. So if that happens, you need to know that so that you can either buy the component that matches your microcontroller, 5 volts, or you can do some type of voltage stepping, put a transformer in between, something like that, to change the voltages and make them match. So these parameters, some of these parameters you need, some of them you don't need that much. Now, integrated circuits are another type of component. There are sort of simple components and more complicated components, and the data sheets vary in complexity. So if you look at a simple component like a resistor, and we'll talk more about those later, but they are very simple, okay? You don't need a data sheet for a resistor or a capacitor. You need minimal information about those components. But more complicated components, the more complicated they are, the denser the data sheet is. Integrated circuits are basically the extreme of that. So integrated circuits, and we've talked about these, microcontrollers are integrated circuits. Integrated circuits are chips. Now, they're typically made of, say, silicon base, but they can be made of other materials, primarily silicon right now. And we're not going to talk about the fabrication technology, except to say that they're basically made on these big wafers. So you can see down there, you can see these discs, these flat discs, these circular discs. So those discs are slices of silicon, and you chop them up into little rectangles, and each rectangle is a chip, right? And so you take that chip and you package it, as you can see over there on the right. You can see the packaging. You hide it inside this bigger package, and the package is used to protect the chip, also to cool the chip as it's running, also to wire its pins. You can see the pins on the bottom. So the pins on a chip are too tiny to contact. So you need them to be bigger, so the package does that for you. So the package provides pins that you can actually make contact with. They're big enough for you to solder into or connect into a breadboard or something like that. So anyway, these integrated circuits, they have data sheets as well. Chips protected by the package. These integrated circuits have data sheets as well, and these data sheets for integrated circuits can be very complicated because what these integrated circuits do can widely vary. And so an integrated circuit, for instance, could be an entire processor, right? And then the data sheet for that can be, heck, over 1,000 pages, right? I've definitely seen that. Or simpler processors like a microcontroller, maybe you get a 150-page data sheet, right? And it's got tons of information on how this device behaves. Now, most of the time for this class, we won't have to go to that level of detail. We won't have to look at the 150-page data sheet and look at the details of what's going on. In fact, with the components that we're using Arduinos and Raspberry Pis. Those boards, they come with libraries that hide the details for us. Okay, so we will not have to be exploring a lot of the details inside those components, thankfully. But you could. So if you really want to make the most use of these components, these chips, you can look in the data sheet and see lots of features. So the trade-off with what we're doing with Arduinos and Raspberry Pis is that they give us these library functions, and we'll talk about these later, that simplify things for us as programmers. But they hide details, they also hide features. So there are a lot of things that you can't do with the processor, with the microcontroller, just because the library doesn't allow you access to that feature. Now, if you want access to that feature, you can go and look at the data sheet and do it, but you won't be able to rely on the nice, easy library functions that you really want to rely on. And inside this class, we probably won't be going into that level of detail about these microcontrollers at all. We'll just use their library functions and not have to worry about these extreme details of the behavior of these microcontrollers. Thank you. So we're going to talk about microcontroller characteristics right now, the different characteristics of microcontrollers. Now, the reason why this is important for making IoT systems is because when you're making an IoT system, probably the first decision or one of the early decisions about how to implement the system is going to be which microcontroller should you use, right? Now, there are a wide range of choices with microcontrollers, and you're going to have to find one to use. Now, a lot of these decisions are sort of pre-done for you. Like if you work at a company, they use a particular brand, we use Freescale, whatever, that's what you use, right? But even within those constraints, you get, even if you're stuck with, say you're only using Freescale, there's a ton of microcontrollers you can use, all with sort of different properties and things like this. And you got to pick the one that's right for your project. Because another feature of IoT systems is that they are generally constrained, tightly constrained, okay? So it's not like a desktop laptop, right? If you look at a desktop, laptop, those things are over-engineered, okay? In the sense that, you know, you get some quad-core processors running at, I don't know, 3 gigahertz, something like this. Regular user doesn't use that, okay? In fact, it's running at sort of 2% capacity 99% of the time. And so you start playing a game. Okay, certain games, they will suck up that power. They will use what the computer has. But vast majority of the time, that processor is sitting there at 2%, basically idling, okay? Because you don't need 4 cores. You don't need that kind of clock rate. You don't need everything that it has. IoT-based systems, those things are cheap, okay? You want to be cheap. You do not want to buy some big, powerful microcontroller that you don't need. You're always saving money, trying to say, look, what is the cheapest thing that just barely does what I need to do? So what you need is you need to have in mind a set of characteristics that your microcontroller needs, sort of the bare minimum from your system, and then you look through the data sheets for the microcontrollers to figure out which one has that, just barely, which is the cheapest one that has that. Now, a data sheet, we're not going to look at a data sheet because those are painful to look at. But a data sheet is basically the sheet that has all the information about the particular microcontroller. So if you ever want to look up a microcontroller, you could look on the top of the chip. You could see the name of the microcontroller, its part number and everything. You type that in into Google, and you say data sheet, and you will come up with a data sheet, most likely. And this data sheet, you might look at one. They are definitely complicated to read. They have lots of different details about the microcontroller. But there's certain information in there, there's certain things in there that we really need to understand in order to make reasonable decisions. So we don't have to understand everything in there, and we will not. But certain high-level characteristics of a microcontroller, you should know what they mean. And so when you look at a data sheet, say the front page of the data sheet, you can at least tell superficially, yeah, it has this, it has that, it has that. That's what I need. Oh, I don't need that, so on. So let's talk about sort of the basic characteristics of microcontrollers that you might look into. And again, also another thing let me mention is that in this class, you won't be making this decision. You're not going to be deciding which microcontroller you're going to use. In this course, we use an Arduino, right? And then the next set of courses, we can use Raspberry Pi. We're set with that. But I'm saying outside of the course, when you want to design your own IoT system, you will need to pick a microcontroller. Okay, so data path bit width. Bit width, what that means is it's the number of bits in each register. A register is a storage element that stores a number. So the bit width basically tells you the size of most numbers in your system. How many bits? So every number is represented in binary as a series of bits, which are binary digits, either 0 or 1. And the more bits, the better. Okay, so what do I mean by that? The more bits mean if you have more bits, like 64 bits, let's say, that means you can get more accuracy than you could with 16 bits, something like that. So you get more accuracy, you get more data throughput. So basically, if you're processing on 64-bit numbers, there's more data processing than you can do than if you're processing on 8-bit numbers. Now, we're not going to go into architecture, but roughly that's what data path bit width means. Now, there's a limit. I mean, you don't need excessive accuracy in your average system, right? So, an 8-bit microcontroller, like the Arduino that we're using, is based on an 8-bit microcontroller. That is sufficient. That is minimal, but that is sufficient for the tasks that we're doing in this class, right? We don't need high accuracy, right? We're just doing simple control operations. We don't need accuracy in numbers. So bit width is something that you have to think about depending on the task that you're performing. Input-output pins. Now, this is actually an important thing because it's often a bottleneck. So you got your microcontroller. The microcontroller is the center of the system. It's connected to everything. It's orchestrating the whole system, right? So the microcontroller has to be connected to all the different components that you want to put in your system. Now, maybe not all, but to a lot of them, okay? And it requires pins to connect it to these things. So maybe you need 3 pins to connect to one integrated circuit and 5 pins to connect to another, and so on, depending on what the circuit is, how many pins it has on this interface. And you can easily chew up all the pins. You can easily use up all the pins in a microcontroller. Because there are these microcontrollers, generally, they don't have too many pins. So you have to be careful about how you use the pins. So that's why very early in the design process, you have to sort of sketch out your design, figure out what the different components are you going to use, and how many pins each one of them needs to talk to the microcontroller. And so you can get a number like, say, okay, I need 40 pins. And then you can find a data sheet that reports that it has at least 40 pins and so on, right? So input-output pins are important for that reason. Performance, okay, so performance is important. It depends on the application, right? So sometimes it's important, sometimes it's not. Now, one thing to note with performance is many times when you're making an IoT device, it is interacting with a human, right? It's a device that's dealing with a human. And humans are slow. So humans, they don't need you to respond too quickly. Now, when I say not too quickly, let's say you're putting images on a screen. These images on a screen, if you put 30 a second on a screen, a human will be very happy with that. A human will see it move, everything will be smooth, right? Now, 30 frames a second, 30 things a second, operations a second is very little for many processors. Now, it depends on the processor. But that's maybe the processor could do a lot more than that, but it's not necessary because the human is slow. So you especially get with this with sound, right? With audio, a human can only hear, 22 kilohertz, I think, is the maximum frequency. That is not very fast, okay? 22,000 operations a second. It's not a lot of, that's not a high rate of processor speed, right? So a processor can process audio data much faster than a human can hear the data, right? So you can use a pretty slow processor and still produce satisfactory audio. So performance is important. You have to consider that. Depends on your application. Video requires a lot more. Even though it's 30 frames a second, each frame might have many millions of pixels, and you might have to do lots of processing on that. So video generally requires a higher rate. But audio, if you're just doing audio or tactile, maybe if somebody's pressing a button, something like that, very slow clock rate is sufficient. There we go. Okay, so some other features. Timers. There are other components inside your microcontroller that are commonly useful to an IoT system, like a timer. Now, you need a timer for any type of real-time application, and a lot of IoT systems have real-time functionality in them. So say you want something to happen at a certain deadline. I want to sample this sound at, every 1,000th of a second, I want to sample a sound. Then you need a timer to trigger that event to happen at that rate, right? So, or I want to sample a monitor. I want to sample some temperature monitor at some regular period, right? You need a timer to set that, to force that to happen at that rate. So timers are really important in microcontrollers, so you need a few timers. And when you're considering the timers, there's a timer accuracy issue. You got to think how much accuracy do you need in the timing, and then that determines the bit width of the timer, right? So an 8-bit timer is less accurate than a 16-bit timer. We'll get into that later when we deal with timers. But anyway, timers are components that you look for. You always want a few of them in a microcontroller. Analog to digital converters. So what this is for is to read analog signals. Now, the issue here is that microcontrollers are generally digital devices. Okay, and when I say digital, all the numbers are zeros and one, off or on. They are discrete values. Okay, 0 or 1, nothing in between. Now, analog is a continuous set of values. So the difference between analog and digital is the same as the difference between real numbers and integers, right? They're discrete integers. You can have 0, 1, 2, but you can't have 1.5. Where analog is continuous. You can have any number anywhere. Now, microcontrollers and integrated circuits in general, they are almost always digital, completely digital. Because it's much easier to design a digital circuit than it is to design an analog circuit. But they are digital. But the world is analog. So what I mean by that, say this light that is in my face while we're recording, right? This light can be a little brighter. I hope it's not a little brighter, a little dimmer, okay? It's not just off or on. They can increase the brightness, decrease it in an analog way. So phenomena that humans interact with, sound, right? I can talk a little louder, I can talk a little softer, and so on. So that's an analog phenomenon. So the world is generally analog to the perceptions of a human, but these computers are digital. So if you want an IoT device to process these analog phenomena, it has to convert it into a digital number. So the brightness of this light, say I want my IoT system to do something when the brightness reaches a certain threshold. It needs to be able to take that analog value of that light brightness, convert it to a digital number that I can use in my code. I can say if brightness is greater than 1,000 or some digital number, right? So analog to digital converters are important in IoT devices because you want to it's very common to take analog phenomena and convert it to digital values that you can process in your code. So A to D converter, analog to digital, A to D, usually want one or more of these in a microcontroller. And I'll note right now, Raspberry Pi does not actually have an analog to digital converter. So that limits it in certain ways. But it is very common for a microcontroller to have at least one analog to digital converter. Low power modes. These are common nowadays too. When I say nowadays, I'm an old guy. So I remember back in the old days when nobody cared about power. There's plenty of power. That's because everything was, things weren't battery powered. Everything was plugged into a wall. Also, microcontrollers were just much slower then, so they didn't consume much power. But nowadays, things are battery driven. Things are fast, right? The clock rate is fast, and the faster it runs, the more power it uses. So power is a very big issue these days when you're doing integrated circuit design and system design. So in integrated circuits, it is very common to have low power modes. In microcontrollers, you can have different low power modes. So the chip doesn't have to be just completely off or completely on. It can have these intermediate modes where certain things are turned on, certain things are turned off, or maybe something is turned on but it's running at a slower rate. Things like this. Maybe you can't use the memory, but it doesn't lose what it's storing, right? So it's got this intermediate state. So there are low power modes built into these microcontrollers commonly. And we're not going to cover that in this class because that's a little more sophisticated than we touch on in this class. But more advanced IoT systems, yeah, you're considering low power modes. These things often run off of batteries. You want them to run a long time and not suck down the whole battery, so that you often want them to run in low power mode when it's possible. So you can see this in a data sheet. You can right in the front page probably it'll say that it has certain low power modes. Communication protocol support. So what this is, and we'll get to this more later, but these microcontrollers, they have to communicate with other integrated circuits, okay? And these integrated circuits, the way that they communicate, they use some kind of a communication protocol. A relatively simple communication protocol. The way that they send data to and from each other over a set of pins, it got to be in a certain order with a certain timing and so on. That's the protocol. And we'll get into more detail about these protocols later, but some of them are UART, I2C, SPI. Those are some, actually we'll cover those later in the class, but these are protocols that you can look in a data sheet and say, yes, it supports I2C, yes, it supports SPI, yes, it supports UART, right? Now this is important because when you're making your bigger system, say you want your microcontroller to talk to some SRAM chip, right? This SRAM chip, maybe it talks I2C, but it doesn't talk SPI. If your microcontroller doesn't support I2C, then you have trouble. Now, generally, these microcontrollers nowadays, they mostly support everything, all the ones I just said, and others too. So generally, you have, in most basic microcontrollers, you have a lot of communication protocol support, but you should check just in case. Thank you. This lecture, we'll talk about microcontrollers in a little bit more detail. Specifically, we're going to talk about the storage elements and how you store data inside a microcontroller. Some of this is important for us just to have an idea of what type of elements there are inside a microcontroller. And not just inside a microcontroller, really, but also the memories outside the microcontroller, because these are important parts of the system, right? You always have data, you need to store it. So we need to know a little bit about that. So first, here's a picture of taken out of a data sheet for an AVR Atmega 2560 microcontroller. This Atmega 2560 is not the same as what's in the Arduino, but it's, or not in the regular Arduino. In the Arduino Uno, it doesn't have this. Actually, I think there is an Arduino that uses one of these. But this is the same series of processors that you find in an Arduino. And here's some of the information that you would find right on the front page of the datasheet. 8-bit microcontroller, up to 16 megahertz, that's the clock frequency. 256 kilobytes of flash memory, so that tells you something about the type of memory in there. Flash memory, as you may know, it's a type of memory that it's non-volatile memory. So after you lose power, when you regain power, the memory is still there. So you see this in thumb drives. Thumb drives are basically flash memory. EEPROM is also another type of non-volatile memory, similar to flash. SRAM is your regular random access memory. We'll talk about that. And then peripherals are, that's sort of a general term for all the other components inside the microcontroller on the chip, like the timers, A to D converters, and all those other things. So it's got a number of peripherals that I didn't list. I didn't put the whole data sheet up there. But that picture right there shows you what the pins look like. So actually where they are configured on the chip. So that means if you bought the chip, then which pin corresponds to which function, and they're all labeled right there. Actually, this is just a snippet of it because we couldn't put all the pins on this one page, but that's like the upper left-hand corner of the chip. It shows you the pins that you can see there, and there are a lot more pins than that, but they're all labeled with names that are referred to later in the data sheet. So let's talk a little bit about the storage elements that you find in these microcontrollers. Storage elements are basically elements that store data, and there's a need for a lot of data, so you need to store data. A variety of types of different data. You can store data, you can store the program itself. The program itself is data, right? So that has to be stored in some sort of storage element as well. And there are different types of storage elements. There's a speed performance trade-off. So some types of storage are very fast, but they cost more. Usually they cost more because of area. They take up a lot more area on the chip, so they cost more. Where on the other hand, there are other types of storage elements that are slower to access, but they cost less. They're much smaller in the chip. There's also a power trade-off that I didn't mention here. So, most basic storage element, fastest storage element is a register. A register, it stores only a single value. Now, depending on how many bits wide the register is, it stores one number. So if you have a 32-bit data path, you'll typically have 32-bit registers. So it can store one 32-bit number. It might be a stores whatever you want, one 32-bit number. Maybe the location in a certain memory location, the value in a location in a memory location, or some number that you're working with, some variable you're working with right now in the program, something like that. Very fast. So when I say very fast, the access time is a lot less than a clock cycle. But it's expensive, so you can't have too many of them on chip because they're so big. So there are several special purpose registers that are devoted to particular tasks on the microcontroller. Like the program counter is a common one. Program counter is the register that tells you what instruction you're executing in the code. It's the address of the instruction you're currently executing. So that's something that you, as a programmer, shouldn't be manipulating. You shouldn't be touching that. But it's a special purpose register. But there are also a set of general purpose registers that your program can actually use for computation, arithmetic, things like that. There's also a register file. A register file is basically a group of registers put together. So these are commonly how registers are organized inside microcontrollers. It acts like a memory, just a very fast memory, right? You can only read one or two of these registers at the same time, but usually you don't need to read more than two in a particular clock cycle. Their instruction operands are stored inside register files. So what you're seeing there is an add instruction. You know, add R1, R2, R3, or 3, R2, R1. It's not going to look like that to you. That's what the machine is actually running, the simple instructions that the machine is actually executing. We'll talk about that a little bit later. But notice it has these operands. So R3 is the destination register. That's the name of a register, R3. And R2 and R1 are the two source operands, the two things that want to get added together. So what this instruction does is it takes the contents of register R1, contents of register R2, adds them together, puts the results in register R3. So commonly, these microcontrollers are reading data out of registers, putting results into registers. Because they're fast, you want to work with registers all the time if you can. Can only read one or two at a time. And you can contain, typically a register file often has, like, say, 32 registers. That's very common to find in a microcontroller, 32 different registers that you can access. So that gives you a hint as to how expensive they are. 32 isn't much, but that's generally all you can afford on a microcontroller. Memories. Now, memories are, you know what a memory is. It stores data. But memories are made to store a lot more data than registers. So you won't just have 32 registers. Memories will be a lot bigger. So there are varieties of memory. One type of memory is called cache memory. Cache memory, it stores a lot of values. Just to give you a ballpark on how big a cache typically is, you know, this is all ballpark for right now, but let's say, you know, a modern processor, maybe you got a 1 megahertz cache. Oh, 1 megahertz, 1 megabit cache. That's ballpark, but say you got a 1 megabit cache, and that can be plus or minus. But that tells you something about how big they typically are. So usually they're a lot bigger than register files, but they're also slower than register files. Where a register file, you could access that in a fraction of a clock cycle. A cache typically takes you a clock cycle to access, a full clock cycle, which is pretty good, but not as good as a register file. Still fast and expensive. They're cheaper than register files, but they're more expensive than larger memories. So that's a cache. And that's on chip. You would find that on the same integrated circuit as the microcontroller. Typically, commonly in the microcontrollers that we're using, they're what's called a Harvard architecture. So you'll have two different caches, at least two. You'll have a data cache and an instruction cache. The data cache holds the data that the program is operating on, and the instruction cache holds the actual instructions of the code that's being executed. So it's common to separate those two. Now then there's also main memory. Main memory is like cache, except it's bigger and cheaper and slower. So you can see the pictures right there of main memory. That's a typical main memory. If you've ever taken your computer and installed memory into your desktop, you'll get something that looks like what you see in the picture. And you can plug it into a slot inside the board. So it's very big, gigabytes of memory, not in the CPU. So it's not on the same chip as by the way, CPU, again, I'm throwing in another term. By CPU, I'm using that the same as a microprocessor and the same as a microcontroller. Okay, same thing, roughly. So main memory is not going to be in the CPU, it's off the CPU. It's on the same board, but it's a different chip, different set of chips. In fact, if you look at that memory, it's multiple chips, right, all put together. It's connected to the system, connected to the CPU via a system bus. So the system bus is basically a group of wires that are basically drawn onto the circuit board, the printed circuit board, that connect the main microcontroller to the memories. Memory access is slow relative to the cache. So what that means is that in a cache, you might be able to access a cache in 1 clock cycle, right? And main memory, maybe you have to wait 100 clock cycles to access a main memory. So again, that's ballpark, but that's not unrealistic at all. There's what's called the von Neumann bottleneck, which is the fact that in a von Neumann architecture, the data and the instruction are all put into the main memory. And the problem is that main memory is much slower than the processor. So main memory, like I say, maybe you wait 100 clock cycles to access something out of main memory. So if you say you want to do an add instruction, you want to add 2 pieces of data that are in main memory, you're waiting 100 clock cycles for that data to show up. And then the add itself takes 1 clock cycle. So all your time is going into memory accesses, right? Or it can go into memory accesses. And that is why people use caches, so that to avoid this von Neumann bottleneck. So the von Neumann bottleneck is the bottleneck to accessing main memory. It's the fact that the memory, it's much slower than the processor. So to avoid that, you basically use the cache. You try to rely on the cache and the registers as much as you can, so that you don't have to go to main memory. Now, all these complexities that I'm talking to you about are you accessing the cache, the register, the main memory, a lot of these we will not be dealing with in this class, because we'll be writing code in either C or in Python. And so all these details about where the data is going to be, is this register going to contain this variable, or is the variable going to be in cache or main memory? All those issues are dealt with by the compiler, if it's C, C++, or the interpreter if it's, say, Python. So we are not going to have to worry about this level of detail as much, but it's important to understand the difference in the different types of storage elements and how they act and how fast they are, how slow they are, so on. Thank you. This lecture will talk about the software side a little bit, specifically how the software is processed before it's actually executed in the microcontroller. So key here is that the code that you actually write isn't literally processed by the microcontroller. It's not executed directly. It has to be processed first, compiled or interpreted, and then it's processed. So we'll talk about that. Software translation. So in the end, a microcontroller, or CPU as we're calling it right here, microcontroller, it doesn't understand C or C++ or Java or Python or any of those languages that most humans program in. It understands its own machine language. So take an Intel processor. It understands Intel machine language, x86 machine language is called. So different processor families understand their own machine language. Now, machine language is basically a set of really small, simple instructions encoded in binary, zeros and ones. So if you ever look at machine code directly, all you see are zeros and ones. Or typically people, when they view it, they look at it in a hex editor. So they see zeros and ones represented in hexadecimal. So but it doesn't look too readable. Basically, it's a string of characters, 0 through 9 and A through F, right? And you just see them in pairs. So it's not easily readable, but that's what the machine actually executes, is this machine code, which is an encoding of very simple instructions: add, subtract, multiply, very basic instructions. Now, above that is what's called assembly language. Now, assembly language is basically a one-to-one mapping from the machine code that's actually executed to a mnemonic, a simple mnemonic that a human can read. And now, it's not easy to read, but it's easier than the zeros and ones. So instead of having a sequence of zeros and ones, assembly code will say add R1, R2, R3, something like that. So that's readable. But still, it's very low level. These instructions are very simple. You can't have, for loops or any of the common constructs that you have in programming languages. You can't use any of that. These are very simple instructions. So assembly language to machine language, they are a one-to-one mapping, right? You have an assembly instruction. It is exactly equal to a machine language instruction. So it's very simple, but at least it's readable. It's in some sort of English-like format. So you can write an assembly language, but it's hard, and we're certainly not doing it in this class. People do it sometimes for certain purposes, but we're not doing it in this class. What we'll work with are high-level languages, what we'll call high-level languages. The commonly used languages: C, C++, Java, ... Python, which is what we're going to look at. We'll focus on C, C++, and Python, but there are many high-level languages that people program in. So these are much easier to use. They give you the regular programming constructs that programmers are used to, loop constructs, variables, structures, objects, things like this. So those languages, high-level languages, are what we're actually going to code in. But that's not what's actually executed. The machine language is what's actually executed. So this high-level code, high-level language that you write in, it has to be converted into machine language before execution. So all the software that you write in a high-level language has to be translated into machine language, into the machine language of the microcontroller, before you can actually execute it. So there's always that process. You're going to write the code, then you're going to do the translation, and then it gets executed. Now, there are two ways this can go, depending on if it's a compiled language or an interpreted language. So compiled language, what happens is compilation happens where the language, the instructions get translated into machine code before execution one time. And you get what's called an executable at the end, which is basically the machine code and plus some extra data, but essentially machine code. And this executable is what is run every time you run the code. So the compilation, the translation from the high-level language to the machine code happened one time before you executed it. And then every time you execute it after that, you don't have to do that conversion. Okay? So compiled languages include C, C++, Java halfway. There are other languages, too, that are compiled languages. So when we work with the Arduino, we'll be working in C++, essentially. So that's a compiled language. So this translation, this compilation process, it happens once. Realistically, it happens many times because you compile it, and then you realize you had a bug, and you fix it, compile it again. But essentially, you finish compiling it, and once you're done and it works, then you never compile it again. You just execute it. Okay? Now, as compared to compilation, there's also interpretation. So you can have an interpreted language, like Java, Basic, Visual Basic. Python is an interpreted language, or a scripting language, but also interpreted language. So in interpreted language, what happens is the instructions, the Python instructions, let's say, are converted into machine code at runtime. So every time you execute that code, you have to convert the Python into machine code. Unlike with the compiled language, right? Compiled language, you compiled it once and you got the machine code, and then every time you executed it, you didn't have to compile again. But with interpreted languages, you have to compile every single time. Or you call it an interpretation, but it's the same thing. You have to convert into machine code every single time. Now, there are advantages and disadvantages. The disadvantage is that it's slow. Compared to compiled code, it's slow because you have to do that whole conversion from high level to low level every single time. But it has a lot of advantages because it allows you, as a programmer, it relieves you of certain burdens. So certain things the programmer doesn't have to think of because the interpreter will deal with them. So for instance, just as an example, let's say in C, you're using a variable, you're defining a variable, an integer, right? In C, if you want to use an integer, you have to declare that integer. You have to say int x, let's say. And you have to put that at the top of your code so the compiler can know, oh, he needs an integer, an x, right? And with an interpreter, like with a Python language, you don't have to declare x as an integer. You can just start using a variable called x. And the interpreter will figure out, oh, I think he means for this to be an integer. I'll refer to this as an integer. Or if it sees you're using the variable differently, it'll make it a floating point or something like that. But that's a burden that the programmer no longer has to deal with, right? The interpreter at runtime can figure out what the type is rather than you as a programmer have to deal with it. So interpreted languages do have the advantage that they are generally easier to program in, but they are slow. Thank you. So this lecture will talk about comparison between Python and C, C++, because Python is what we're going to be using with the Raspberry Pi, C++ we'll be using with the Arduino. Also, we'll talk a little bit more detail just to understand the contrast. We'll talk about the tool chain, the software tool chain, all the tools that go into taking a high-level piece of code and getting the eventual machine code. We'll just look at that whole picture because it ends up looking a little bit different for one versus the other. So Python is an interpreted language. It's a scripting language, but that's also an interpreted language. It's high-level language. It's easier to work with because it's interpreted. So there are certain things the programmer does not have to deal with, like the type of variables. Is it an integer? Is it a floating point? Is it a string? You don't have to worry about that in Python. Python figures that all out based on how you use the code, how you use the variable. So at runtime, while it's executing and doing the interpretation, it can figure that out. Other things too, like memory management. In C, C++, you have to deal with that. You have to say, look, I need more space. There's a function called malloc. You can allocate more space. I need more memory for this variable. Python, you don't have to say that. It'll just make it for you, right? And when you're done with it, it'll get rid of it. So when you're in C, you have to make it explicitly, and you have to, as a programmer, have to know, oh, now I'm done with it. Let me free that memory. So there are a lot of these burdens, these programming burdens, that you don't have to deal with in a language like Python because the interpreter is there to take care of it for you at runtime. Now, comparing that to C, C++, C and C++, they're related languages. Actually, C is a subset of C++. So C came first, C++ came second. C++ is a superset. So C++ does everything that C does. So if you have a C compiler, a C++ compiler, it'll compile any C code. But C and C++ are compiled languages. So you write the code, you compile it once, and then you get an executable, which is machine code plus extra information, and you only execute the machine code. You don't have to do the interpretation at runtime. So as a result, C, C++ programs are generally a lot faster than Python programs, but the programmer has to deal with a lot more details. Now, dealing with a lot of details is hard, but when it comes to embedded systems, it's often useful because sometimes, not just sometimes, often, the programmer, an intelligent programmer, can write code more efficiently than the Python interpreter can. Okay? So the programmer, knowing something about the behavior, what the behavior they expect, they can write their C, C++ code in such a way that it runs a lot faster than the Python interpreter could ever predict. Because the Python interpreter, it's dumb compared to a human, right? A human can know something more about the context in which the software is being used. So C and C++ are commonly used in embedded systems. Outside of embedded systems, you see them used less. Maybe Java is favored or something like that. But because of the level of control that you get with C, C++, they're much more commonly used in embedded systems. So compilation. This is what compilation looks like roughly. At the top, you've got say some regular C code. And actually that code is pretty generic. You can have A equals B plus C in any number of languages. Java, Python, they look all very similar, except for the semicolon at the end. That could have been Python, right? So you got the high-level language at the top. And in the end, you want to get what you see at the bottom, a sequence of zeros and ones that represent the instructions. So what happens is if you look at that top instruction, it's actually broken down into a set of smaller steps, of smaller behaviors. So that instruction, A equals B plus C, that actually it's not just an add instruction. It's not just an add that will be performed. First, you got to get the B variable, you got to get the C variable, you got to add, and then you got to put the result back. So maybe B and C are in memory somewhere, and A has to go to memory. So first, you got to load A from memory, or load B from memory rather, then load C from memory, then do the add, then store the result back in memory for A. And that's why you got 4 instructions in there in the middle. You got 4 what you call assembly instructions. So the compiler will make assembly instructions. The load LW is load word, so it'll load B into memory. Then the next LW loads C into memory, and specifically into the registers R1 and R2. Then the add takes R1 and R2, adds them, put the results in R3, and then that last instruction SW, store word, that takes what's in R3 and puts that back into memory, wherever you want A to go. So that one high-level instruction breaks down to 4 simpler assembly-level instructions. And then the assembler takes each one of those 4 instructions and converts it into a sequence of zeros and ones. So you can see at the bottom, you see actually 1 instruction, just the add instruction. But presumably you would have 4 instructions, 4 sequences of 0 and 1s, just like that, to correspond to each one of the 4 assembly instructions. So that's the process of compilation, a very simple version of it, but you take the high-level language, in the end you get a sequence of zeros and ones that represents the instructions that need to be performed, and those zeros and ones are what get interpreted by the microcontroller. So this is a high-level view of your standard tool chain, software tool chain. A tool chain is basically a term that's used in embedded systems a lot and in IoT devices a lot that describes the sequence of tools, of software tools that you have to use in order to convert a program that you code into an executable program on the platform. So if we look at this picture, we start off with the host up at the top left. The host is laptop, desktop, whatever it is that you're actually writing the code on. So you write your code on the host using some text editor, it doesn't really matter which one. Then this is actually a compile tool chain. So you write your code, let's assume it's C. The C code comes out of the host, it goes into a compiler. So the compiler, actually I should have said here, this is what's called a cross compiler. So a cross compiler is a compiler, it takes the C code and converts it into assembly code. Okay? But the assembly code is for the target platform. So the target platform is whatever microprocessor you're targeting. So let's say I'm using an Arduino, right? The processor on there is going to be an AVR Atmega processor. So the compiler is a cross compiler. It'll compile and make assembly code that works for that AVR Atmega processor. So the compiler makes that. Then that code goes into an assembler and gets an object file is generated, which is actually machine code. Okay, again for the target platform, for the AVR Atmega, whatever it is. So the OBJ file, the object file, that has the machine code plus extra debugging information and other assorted information in there, but it has the machine code. Now you'll notice that there's a path on the top from the host into the assembler, assembly code. You could write assembly code directly. So you could write C code, which is what we'll do. You could also write assembly code directly. We will not do that, but you could, and that would get merged in at the assembly phase. So then once you get the object file still, that describes all the code that you wrote, but remember that we're using library functions all the time. And we haven't done this yet, but in our code, you always want to use library functions to handle complicated tasks. Now, library functions are really just functions that are pre-written, but you didn't write them. You just call the function. You just write the name of the function, and that code gets executed. So all those library functions have to get integrated into your program at some point, and that's what the linker does. So the linker, we don't see this in the picture, but the linker, it has access to all the libraries. And the linker basically takes the library's code and inserts it into your code at the appropriate places. It creates links between your code and the library code that you use. And then the output of the linker is going to be some executable program. Now the standard path that we're going to use is from the linker to the programmer, which then goes to the microprocessor. So the programmer, what that does is it takes the executable code and copies it, writes it from the host machine onto the microprocessor, usually into the flash memory of the microprocessor. Because in order for the microprocessor to actually execute the code has to be sitting on its memory. So that's what the programmer does, and that actually goes on via USB cable for us, right? The programmer will take the code, send it across the USB cable, and write it into the target, say Arduino for us, or Raspberry Pi, or whatever it is. So that's a programmer. There can also be another path, a debugging path, where if you're using a debugger, which is a little more sophisticated than what we're going to deal with, you can take the executable and write it into the target platform and write debug code in there too, and control it during execution. You can set breakpoints and things like that. We won't cover that right now. Thank you. This lesson, this lecture, we'll talk about operating systems a little bit, what an operating system is. Now, they're not always present in IoT devices, and in fact, with the platforms we'll be working on, we'll be working with an Arduino and a Raspberry Pi. With an Arduino, you do not have an operating system. It's really too slow to support that. But Raspberry Pi you do, typically. So we'll talk about the role of an operating system in an embedded system and an IoT device. You may or may not need it. So an operating system, it's an extra layer in between the program, your application code, and the actual hardware. So, so generally, say we were working on an Arduino, right? There's a user at the top who's using some application, right? And this application, by application we mean the actual program, right? So you've compiled the program, and that application, that's the application code. Now, if it were an Arduino, that application code would connect directly to the hardware. So it would go straight from the application to the hardware, no operating system at all. And the application directly controls the hardware, sets signals high and low, and so on. But in, say, a Raspberry Pi or a more complicated IoT device, you would have something like what you see here, where the user talks to the application code actually may not directly connect to the hardware, it communicates with the operating system. So it makes calls from the operating system and requesting hardware service, and then the operating system manages the hardware most directly. So that's where an operating system fits in the picture, that the code that you write and compile, the application code, that interfaces with the operating system, and the operating system deals with the details of interacting with the hardware. So it manages other programs. So one thing about an operating system is that it allows you to have not only one application, but many applications. So you can run lots of different applications at one time, and the operating system itself manages the hardware. So it gives them turns, lets them take turns, and stuff like that. And you see this in standard operating systems like Windows or in iOS or something like that. You run, typically on a laptop, desktop, you run many programs at one time. And the operating system allows you to do that, right? Without an operating system, you can only run one program at a time. So you can execute a lot of programs together, and when you're executing together, remember they're not actually executing together, they just seem like it. So it's really alternating, but very fast, faster than a human would really notice. So it looks like they're all running at the same time. Nice user interface. So often, now how nice a user interface really depends on the operating system. If you look at a desktop or laptop, Windows, iOS, Linux, something like that, they will have a very nice user interface, a graphic user interface, GUI. You can double click on something, double click on a file, it'll open it up, that sort of thing. That's a full-on operating system. The operating systems that you find in an IoT device, they're much smaller and stripped back. So they're not likely to have any graphical user interface or anything like that, but they will have a user interface, a command line. So if you ever use a Windows command line prompt, or iOS, you use a terminal window, Linux, you use a terminal window, something like that. I call that a nice user interface. It's text-based, but it's nicer than not having it. So there's a user interface that's provided of some kind. And it needs processing power. So one thing about operating systems is that operating system itself is a big program, right? It's a big program that's running in addition to the actual programs that you want to run on your IoT device. So it's going to consume clock cycles, right? There are some clock cycles that are spent doing operating system tasks, right? Some memory that's spent storing the operating system data, things like this. So the operating system itself takes up resources. So you have to make a decision as to whether you need one or not, because it's going to cost you resources, which means cost you money. It slows down the system because the operating system, while the processor is working on the operating system, executing the operating system code, it can't be executing your actual application. So it slows things down, and so as a result, when you use an operating system, you generally need a faster processor. That's why if you look at an Arduino, which is running at maybe 8 megahertz, something like that, you usually don't support an operating system with that. But if you run a Raspberry Pi and you've got like 1 gigahertz, then it's okay to support an operating system because it has enough clock cycles that you can do that. A little example of an operating system that I had a student group do something like this, do a project like this several years ago, where they wanted to have a web-controlled car with a camera. So it's an RC car controlled through the web. So you can go to a laptop, desktop, whatever, anything that has a Wi-Fi, could go to a phone, open up a browser, and connect to the car. And the car has on it a camera and its own web server, right? So you can connect to its web server and control the car through its own web server. So it has an interface that looks roughly like what you're seeing down here. On the one side, there's a picture, the image of what the car sees. So that's actually coming from the car's camera. So like I said, the car on it had a camera that was connected to a web server. So the view from that camera would be streamed through Wi-Fi over to whatever your browser device is, right? Then it would have buttons forward, back, left, right to control the car. So you click forward, it would move the car forward. Click back, it would move it back, and so on. So you can send commands to drive the car through Wi-Fi to its web server, to the car's web server, and that would directly control the steering and the motors and all that. So in a system like this, it's useful to have an operating system because there are so many things going on at one time. So the car is controlled over the internet, Wi-Fi generally. The car has its own web server, which has an actual a URL address. And the web interface allows you to control the car and see the images and so on. Also, it has an auto brake feature to avoid collisions. So it'll stop automatically regardless of what your controls are. If it senses something in front of it, it'll stop. But the idea is that it generally has a lot of tasks to do, a lot of things to do at one time. And in that type of situation, an operating system can be very useful. Thank you. So this lecture, will talk about a little more about operating systems and what they do. We'll talk about task and process support, really, about how operating systems support multiple tasks executing at the same time and how that's useful in certain IoT devices, in more complicated IoT devices. So multiple tasks. So this is actually going back to the last lecture where we were talking about this embedded system that I had my students make. Actually, IoT device. It was a web-controlled car. And through the internet, you could go to a browser, open up a browser, and remotely control this car. So you could view what its camera was seeing on your web browser. Also, you could hit some buttons, forward, back, left, right, to control the motion of the car. And so the car itself has its own processor and a web server running on it. A Wi-Fi web server running on it, and a camera, and it could manage all these tasks. These tasks could be managed remotely. But the idea is that on that car, on its microcontroller, it had to do multiple things at once. Okay? There are multiple tasks that it had to handle. In order to do this, that it had to handle at the same time. So let's look at some of these. One thing is sending video data. So this car, it was constantly, if you were connected to it, it was constantly sending video data from its camera to your phone or whatever your web browser was running on, right? So it had to do that, send video data all the time in the background. Then servicing the motion buttons. So in the interface, you could go to your web browser, hit the forward button, the car would move forward. Hit the back button, the car would move back, and so on. So the car, its microcontroller has to service those buttons. So even while it's playing the video, at the same time, if somebody presses forward, it's got to respond, go forward, go backward, and all that. So it has to do that. Detecting obstacles. So this thing has an auto brake feature, so it has to be constantly detecting obstacles. So if there's an obstacle in front of it, it will brake. Regardless of what the commands are, that would get overridden. So it's got to be constantly detecting obstacles while it's showing its video and while it's responding to the buttons, the control buttons. Also, auto brake. So that's another thing that has to happen concurrently. You can be showing video, somebody can be pressing buttons, you can be responding to them, but if you detect an obstacle, you got to brake automatically, concurrently with the video and with everything else. So multiple tasks have to be performed by this device. And in a situation like this, it is helpful to have an operating system to handle the multiple tasks, to help you handle them. So what happens is, just talking about how they can happen together, you can detect and auto brake cannot occur together, right? So if you detect, then you auto brake. They don't happen together, but everything else can happen concurrently. So in a situation like this, you need to have multiple things running at the same time, multiple tasks being performed at the same time. Now, you could, as a programmer, write a relatively complicated program that does all these things at once and checks, while you're sending video data, it's also checking to see if a button is pressed, it's also checking for collisions and so on. But an operating system makes this easier because you can write each one of these tasks as a separate task and then let the operating system intermix them. So you can write one piece of code that just sends video data, another piece that services motion buttons, another one that detects obstacles, and another one that does auto brake. And then you can give them to the operating system, and the operating system will make sure that they all run at the same time. They don't have to, as a programmer, you can write things separately. You can write the sending video data code separately from the servicing motion button code, right? And the operating system can interleave them for you, and that relieves a lot of burden from the programmer. So the main job of an operating system is to support a process or a task abstraction. I'm not going to differentiate them too well right now, but let's just talk about processes. A process is an instantiation of a program, so a run of a program. So if you got a program, PowerPoint, let's say, which is running on this machine right here, there is a process. When you're running PowerPoint, it has a process running. And so say on my machine, I open PowerPoint 10 times, right? Then I've got 10 different processes, all instantiations, different instantiations of PowerPoint, right? So a process is like a runtime instantiation, an execution of a program. And you can have many of them at the same time. So the process has to have access to the resources of the processor, the CPU, meaning the microcontroller itself, the memory, right? So a process needs to read from memory, write to memory, and so on. Other resources, the timers, the A to D converters, the network access, all that, the processes all have to access that. But they have to share that, right? So there might be only one A to D converter in this microcontroller, and there might be 3 processes that need to use the A to D converter. So the operating system, part of its job is to manage all these resources, to make sure that everything gets used fairly one at a time. So if all 3 processes want to use this A to D converter, the operating system essentially puts them in a line, says, okay, you were first, so you go first. You're more higher priority, so you go second. Right? The operating system's job is to manage all these resources, the memory and the CPU and I/O and A to D converters, all the resources in hardware. The operating system takes care of that and makes sure that the different processes can use them in a fair order. Thank you.